Nothing is. When it is at a very, if at all, it is at a very far point. When it is at a very far point, clear. Let's say this is covering this much amount of area. Then in the same time, when it is close over here, it has to cover the same area because the radius is small. Because the radius is small, what we can say that distance covered by the angle swept by it will be large. Do you agree?
Yes, sir, but the area will be still the same, right?
Area will remain same.
But the angle through which it transfers will be different.
Yes, the angular displacement will be different. Why? Because here, if this distance is r1, this distance is r1 and that distance is r2. So if I say that this distance is r1, this distance is r2, what is happening is that r2 is greater than r1. But here, what we know that the angular momentum, that means aerial velocity, r cross v must be constant. Is that right? In fact, if at all numericals are asked on Kepler's law, one of the numerical can be this also. Never forget this relation. dA by dt is angular momentum by 2. So here I can say that it is having some velocity, perpendicular velocity v1. Here I can say that it is having some perpendicular velocity v2. Here, so since the aerial velocity is constant, that means product of r and v is constant. R bar cross v bar is constant. So here these two are perpendicular. Clear? So what we can say is that let's consider this point as P1, or yeah, these two locations, these two areas. So here, if this area is A1, if this area is A2, clear? If the times are constant, then we can say that dA1 by dt is equal to dA2 by dt, which is a constant. Now we know that this is 1 by 2 r cross r1 cross v1, that is equal to 1 by 2 times r2 cross v2. Now, since R1 V1, the R and V they are perpendicular, I can write it as R1 V1 is equal to R2 V2. So, from this relation, what we can claim is that since we can say that since R2 is greater than R1, this implies V1 is greater than V2. Understood? That means when it is very close, it will travel faster. When it is very far, as it is moving away, it will travel at a slower rate. In fact, that's what we can see from the length of the arrows. Okay, the vectors here we can see that this one v1 is larger, whereas v2 is smaller, v2 is short. Is that okay?
Sir, if we multiply both the sides by m, will it show that the angular momentum remains constant at any point?
Yes, that's what here we have said, right? Angular momentum divided by twice that of mass is constant. However, mass is a
Okay,
constant.
sir.
Mass of a planet is not going to change. That means angular momentum is constant because there is no torque acting on the particle.
Yes, sir.
Is it done?
1 minute, sir.
1 minute. Done, sir.
Unfortunately, in this slide, the space is not left. So I'll be writing the Kepler's third law in the next slide. Is that okay?
Okay, sir.
This is Kepler's third law. This is what is called law of periods. Look here, it says that assume that you see, we can say that elliptical path is also like a circular. I mean, circular path is also a special case of elliptical path, right? So
Yes.
he has done it for this. This is for satellites. Okay, you can express the same logic for what? Same logic for planets also. Now, assume a situation that if this is the sun, okay, assume that if this is revolving in circular path, this is sun. Now assume that there is a planet over here. This is of mass capital M. This is of mass small m. Now definitely both of them will attract each other with gravitational force of attraction. This is Fg. This is Fg. Now let's say the radius of the circle is r. Radius of the circle is r. Let's assume that this is moving with a velocity v. That this is moving with a velocity v. Speed v. Another thing is that we know that if this is revolving in circular path, someone must supply the necessary centripetal force. Is that right?
Yes, sir.
Yes, sir.
For circular motion, Fc must be equal to mv square by r. Is that right? Yes. So what is the value of Fc? Fc is nothing but Fg, that is G m1 m G capital M small m by this is r is equal to this is mv square by r, where this v is nothing but the speed with which it is revolving in orbit. In fact, this must be called as orbital velocity. Okay, we'll find it out that this is orbital velocity, or if you want you can leave it as v also, not a problem. That is nothing but the velocity with which it is moving in that particular orbit. Now coming to here, you can cancel the mass. So what's the velocity? V square is equal to here g capital M small m by r square. So r gets cancelled. This will be
Root
g
GM by
capital M by r. In fact, yeah. So let's put this v as this one. Here itself we have done it calculated for orbital velocity. That turned out to be how much? G capital M by r for any orbit. Now, if you want to calculate the time taken for it, time period, let's say it's starting at t is equal to 0. Again, it is reaching here at a time t is equal to t. So, time period t is equal to total distance traveled by speed. Is that right?
Yes, sir.
Uh, yeah, total distance traveled by speed. So, this will be 2 pi r by under root gm by r. So, this can be write as 2 pi by under root g times r power. This goes to the numerator, r square times r power 1 by 2. Can we say that this is r power 3 by 2?
Yes, sir.
Yes, sir.
Understood? So from this, it says that is, from this we can claim that t is,
Sir, you forgot the M.
yeah, correct, r power 3 by 2. Now from this we can say that t is directly proportional to r cube power 3 by 2. Clear? R power 3 by 2 or t square is directly proportional to r cube. So this relation is what is called Kepler's third law. I mean to say, yeah, that is Kepler's third law says that the square of time period is proportional to cube of the radius, mean radius, or average radius of an orbit. That's what Kepler's third law says. square of time period cube of what is this? Yeah, cube of radius. Understood the logic?
Yes, sir.
So this 2 pi by root g, that's the Kepler's constant, right?
Yeah,
It'll be constant for all planets, right? Because it doesn't involve any of the individual planet masses.
it doesn't involve any planet's mass, but if at all you are talking with respect to motion of planets, then that's the mass of sun. If you're talking motion of satellites, that depends on the mass of the planet.
Mass of planet. Okay, sir. Done, sir.
Now let's talk about orbital velocity. Assume that if a satellite or planet is revolving around sun, or else let's talk. We can express this with orbit also for satellites also. Clear? So let's solve it with respect to satellite. Let's say this is surface of the earth. Clear? This is the earth. The mid center one is earth, and that the outer one is the orbit of satellite. Let's assume that this is the radius of the earth, which is r. Clear? Now from that r at a height h, you are talking about a satellite which is revolving with some speed v naught. Clear? So this r plus h is nothing but what? R plus h will be nothing but the radius, is that right? Radius of the orbit.
Yes, sir.
We call it as r naught also. That is r naught also. Now, if you want to calculate orbital velocity, here itself we have done the same logic. If something is revolving in circular path, definitely someone must exert necessary centripetal force. So this is Fg. Here, this is Fg. Now, what we can say is that since Fg is equal to, yeah, since Fc is equal to mv square by r for circular motion. So this will be Fg, that is equal to G capital M small m by r naught square is equal to mv naught square by r. So from this, what will happen? You can cancel value of small m. So r naught gets cancelled. So this will be v naught is equal to under root G capital M by r naught. Clear? So this is what is called orbital velocity. Clear? Now the thing is that if h tends to 0, if h tends to 0, that means very close. If the satellite is uh, revolving very close to the Earth, that is what is called low Earth orbit. Understood? That means h is very close, or we can say h is much less than r. Not h tending to 0. Let's say h is much less than r. That is nothing but for a low Earth orbit. Low Earth orbit, what we can say, uh, because that is nothing but V naught is equal to under root Gm by R plus H, right? So if you neglect this, that will be nearly equal to Gm by R.
It will be root gr.
Yeah, root Gm by R, that will be nothing but equal to how much? Under root G small g capital R. So this will turn out to be somewhere around
8 kilometers per second, right?
yeah, nearly 7.8 or 8 kilometer per second. Understood? So this is for a low Earth orbit. For different orbits, the velocity will be different. So in fact, what you can observe is that since here, what we can observe is that this was this was just a special case. This was just a special case. Now, since V naught is equal to under root Gm by R naught, we can say that V naught is inversely proportional to under root R naught. So as R naught increases, what will happen to the velocity of V naught? Orbital velocity decreases. That means as you move away, what will happen is that the time period increases. Is that right? Because distance traveled is increasing, time period is velocity is decreasing. So what must happen to time period? That is, time period is proportional to r naught over 3 by 2 in that particular orbit. So time period increases. So they will move slower. Whereas coming to the closer orbits, they'll move faster. So mostly questions will be based on this logic only. Like if at all there is a planet revolving in a radius r naught, okay, where at a height h which is equal to r. Now, if you want to take it to a height which is equal to 2r, how much additional velocity you must give it, or how much an additional energy it must be given.
So could you explain the last line you wrote once again?
I'm saying that the planets which are the satellites which are close, or the planets which are close to sun, they revolve faster, their time periods are less. But as you're moving away, what is happening? The radius is
Time
increasing
period
and
increases.
the velocity is increasing. That means the distance that needs to be covered is increasing in one full revolution, whereas that means what must happen? Distance is increasing, speed is decreasing, so time taken must increase.
Increase. Yes, sir.
So the planets revolving in larger radius move with less speed and will take more time.
Okay, sir.
Children,
Yes, sir.
now here, if you try to calculate the energy of an satellite or planet, energy of a satellite or planet, what we can do? We know that energy is nothing but kinetic energy, orbital kinetic energy. That is how much? Half m v naught square, right? Half m v naught square. Usually, the thing is that we know that it is not that the satellite is revolving around the planet. The planet and satellite, both of them are revolving around their about their common center of mass. But because here the mass of the planet is so huge that the center of mass is almost at the center of the planet. That's why we feel that the satellite is only revolving, but in reality, the let's say Earth and Moon, they are revolving about their common center of mass. You should not forget that point. So this is half m v naught square. That means half m. What do you know about v naught? V naught is nothing but under root. Sorry, v naught square. Can I write it as g
GM by R.
GM by R naught.
r naught? Okay. That means g capital M small m by 2 r naught. 2 r naught is the kinetic energy. Let's consider this is equation 1. What's the potential energy of the orbit?
Minus G capital M small m by R naught.
Very good. Minus g capital M small m by r naught. Clear? So that is equation 2. What's the total energy of the orbit? Total mechanical
K
energy.
naught plus U naught.
That is kinetic energy plus potential energy. What's the value of kinetic energy? G plus g capital M small m by 2 r naught. Now, can I write this as minus 2g capital M small m by 2 r naught?
Yes, sir.
So this is 1 minus 2. That will be equal to how much? Minus. That is
Minus G capital M small m by 2 R naught.
2 r naught. Yes, that is correct. So
Yes, sir.
the energy, you can say that this is minus times that of k naught, or you can also say that that is u naught by 2. Is that okay?
Yes, sir.
So total energy of a satellite in an orbit, that is how much? That is minus k naught, that is equal to u naught by 2. In fact, or else you can say minus g capital M small m by 2 r naught. That means energy of a satellite in an orbit is what? Negative. Energy of an satellite in an orbit is negative. In fact, because energy of a satellite in an orbit is negative, it is something like an electron which is revolving around nucleus. In fact, in the few in 12th when we go, we can see, or else in chemistry you might have already studied that the energy of an electron is negative. So this energy you can
Yes, sir.
consider as binding energy also. That means this satellite is bound to the planet with this much amount of energy. If at all it wants to become free, you have to supply that much amount of energy, then only it can become free. Is that okay? Just like a electron, you supply ionization potential, that will become free. So here also we do the same thing. Got the point?
Yes, sir. Sir, so what is the maximum value of energy that a satellite can have, sir? Is it zero?
No, no, no. You can have positive values also. You see, once it becomes free, potential energy will be zero. So kinetic energy can be anything, right?
Yes, sir, understood. Sir, while revolving around the planet, the work done by the satellite will be zero, right?
Yeah. On the planet, the work done by the satellite will be zero. That's the reason why its kinetic energy or the overall energy will remain constant.
Okay, sir.
It's not getting affected. So we are left with one last topic in this gravitation, that is how to launch satellites into our orbits. Clear. So what will happen with various speeds? So if you are sending, if you are shoot, that means we always shoot a satellite right into air. So what happens if you shoot it with less speed, with moderate speed, with high speed, and with very high speed?
Sir, this we proved mathematically that energy is negative, but like in general terms, why is it negative?
Why is it negative means you see, actually if the energy was positive, it can move in whatever way it wants. But is it able to move in whatever way it wants? No. It is being forced by the planet to revolve in the circular orbit. Is that right?
Yes, sir.
It means it is something like binded to the planet, right?
Okay.
You got the point.
Yes, sir.
It happens like it is restricted now. It has to be there itself. It cannot go outside. It is
Okay.
something like this. Let's say you are having surplus money in your account. You can go wherever you want, whatever country you want. But let's say you owe me some money. Would I let you go out of the city?
No.
It's something like that. This
Okay.
this planet is in depth. Understood?
Okay.
It is
Yes.
to give some energy. So if you want to separate them, because what happened was that this planet it started pulling the satellite from inside to here. It has done some work on it. It has invested some money on it. So if you want to make it free, then we have to drag them away, right?
Yes, sir.
Under mutual gravitation of attraction, they're revolving. To overcome the gravity, instead of colliding, they're rotating. About the concept of mass, that's good. But if you want to separate them, you have to do some work on it.
Okay.
You do some work on it, and that will come out. That's it.
Yes, sir. Got it.
So let's conclude today's class over here. Tomorrow's class, we talk about launching of satellites.
Okay, sir. Thank you, sir.
Okay, sir. Thank
Thank
you.
you, sir. So evening
Let
3:30 to 4:30, right?
Yes,
sir,
Okay,
please
sir.
send the
Thank you.
recording.
sure.
Yeah. Thank you.